Hello everybody and welcome back to the channel. I'm here with an A-level chemistry video where I'm going to explain percentage uncertainty to you. And this is particularly important for questions, for instance, about required practicals or PAGs as some courses call them, because there will always be a 2 or a 3 mark question relating to percentage uncertainty. In order to do that, we'll take a look at what uncertainty actually is, the difference between a reading and a measurement, and then most of my time on the video will be looking at how you calculate percentage uncertainty and how you use percentage uncertainty in questions. For instance, how do you reduce the percentage uncertainty, or how do you comment on the accuracy of a particular experiment? And we'll explore those ideas and then we'll apply them to 6 questions at the end of the video, which you can download yourself in the description and have a go at that yourself. And then once you have had a go at the questions, you can watch me talk about the questions and mark your answers yourself. In A-level chemistry, we need to know that every measurement that we make has some kind of inherent uncertainty to it. And what that means is we can't ever really be 100% sure that the value that we've recorded is exactly the true value. No, the true value is likely to lie within a range of possible values for any given experiment. And how big that uncertainty is depends on a number of things. For instance, what type of instrument are we using and what is the resolution of that instrument? And resolution is what's the smallest value that this piece of measuring equipment can actually record. Maybe the procedure itself has some kind of uncertainty to it, and we can try and modify a procedure to limit the uncertainty by carrying out repeat measurements. And sometimes an experiment has a requirement for you to make a judgment, and we can never be totally certain that our judgment is 100% correct or that the timing of the judgment was always correct. Now we should look at some specific examples of uncertainties. And before we can do that, we need to clarify something about the recordings that we might make during an experiment. First of all, there are readings. Now, a reading is a value that you make from a single judgment using a piece of equipment. So, for instance, what volume of liquid do I have in that measuring cylinder? What is the temperature that I am carrying out this experiment for? What is the volume of liquid in this volumetric flask? What is the pH value using a pH meter? These are all readings that you can make during an experiment. And so, for instance, if that measuring cylinder had been measuring 25 cubic centimetres of solution, but the uncertainty was plus or minus 1 cubic centimetre, that means we might have anything from 24 cubic centimetres to 26 cubic centimetres. That is the extent of our uncertainty. We thought we were measuring 25, but because this uncertainty is plus or minus 1 centimetre cubed, we might have anything between 24 and 26. And similarly, if we're measuring the temperature of the room today and we think it's 15 degrees C, that might be anything from 14.5 degrees C to 15.5 degrees C, because the uncertainty in our particular thermometer is plus or minus half a degree Celsius. And so what that means is our recording that we've made, our reading that we've taken, is typically quoted as being 15 degrees C plus or minus half, or 15 plus or minus half a degree C, or our volume might be 25 plus or minus 1 cubic centimetre. Similar to that, but really importantly different, there is something called a measurement. And a measurement is actually at A level taken to be a value that is measuring the difference between 2 judgments or 2 readings. So in other words, in order to arrive at this value, we have had to make 2 readings. And so an example of that is, for instance, simply using a ruler. If you're using a ruler, you have to line that ruler up at one end of a particular substance, and then when you read off the ruler, you're making a judgment about the other end of whatever it is that you're measuring. So actually, you're judging 2 values when you're using a ruler. Another measurement is using a stopwatch. If you start the stopwatch and you stop the stopwatch, there was uncertainty in both the starting time and then the finishing time, and that's linked to reaction times. And so if we just return to that ruler example, if we think we are measuring something that is 12 centimetres long, but each end of that ruler has an uncertainty of 0.1 centimetres, that means that the reading on the left-hand side might not be correct, and then the reading on the right-hand side might also not be correct by the same amount, 0.1 centimetres, that they could be out at both ends. And so that means that the measurement, 12 centimetres, has got an uncertainty of plus or minus 0.2 centimetres. What we have to do is we have to double that, what's called the absolute uncertainty, and instead of it being 0.1, it is 0.2. It's also considered to be a measurement when you're calculating a change in a particular quantity. Maybe you are measuring a temperature change. Maybe the temperature starts at 20 degrees C and increases to 35 degrees C. So the change that you've measured is a 15 degrees C change. But in order to arrive at that change, you had to measure 20 degrees C and you had to measure 35 degrees C. And so both of those carries some kind of uncertainty to it. And so there's uncertainty twice. In the same way, if you're measuring a change in mass, maybe you've measured the amount of substance in a particular beaker, you've measured it as 200 grams, and then you pour some substance out of that beaker, and now it has a mass of 198 grams. And so what that means is you've added 2 grams of a particular substance from one beaker to another, and that's the mass change. But both of those measurements that you were making could have been slightly wrong. That 200 and 198 might have been slightly wrong. So there were 2 uncertainties. And so if we start to apply the uncertainty which we did with the previous examples, if the first temperature reading was accurate to the nearest plus or minus half a degree C, then that means that this value might be out by 0.5 and the second one might be out by 0.5 as well. And so since the uncertainty is multiplied by 2, the total uncertainty for this temperature reading is plus or minus 1 degree Celsius. And so overall, our final value for a temperature change is, the temperature change is 15 plus or minus 1 degrees Celsius. And then in the same way, if the uncertainty with the 200 gram mass is plus or minus 0.2 grams, for instance, and there will also be the same uncertainty in the 198 gram measurement. And so overall, we have to double that uncertainty because we could be as much as 0.4 out if each one of them is too high, or if one of them's too high and the other one is too low, in fact, then that means that our measurement could be anything between 1.6 grams and 2.4 grams. And that's because the difference between this upper value and the lower value is 2.4, whereas the difference between the lowest value here and the upper value here is actually only 1.6. And in the same way, our temperature change could be anything between 14 degrees C and 16 degrees C. When you are making repeat measurements during an experiment, which is really, really common, it is sometimes necessary to quote the uncertainty that is inherent in that process. And you might remember this from GCSE level. That's the only time uncertainty is mentioned at GCSE level. And the uncertainty is taken to be plus or minus half of the range. And that means, for instance, if you were decomposing a carbonate and you were looking at the mass of carbon dioxide that was produced in each case, and you did this 3 times, and you got 3.2 grams, 3.3 grams, and 3.6 grams, then the range of your data is between 3.6 and 3.2. And so the difference there is 0.4 grams. And so half of that range is 0.2 grams. And so when you calculate your mean value, that mean value is taken to be accurate plus or minus 0.2 grams. In other words, half of the range. The most common thing you could be asked to do with uncertainties is to calculate a percentage uncertainty. Now that is found by taking the what's called absolute uncertainty, so that's the plus or minus value that you get given in a question, divide that by the measurement that you're making, and then multiply it by 100 to turn it into a percentage. So, for instance, if you are measuring 25 cubic centimetres of solution using a measuring cylinder with an absolute uncertainty of plus or minus 0.5 cubic centimetres, the percentage uncertainty is found by taking 0.5, dividing it by 25 and multiplying it by 100. So that gives you a 2% error. And what that means is that you, through no fault of your own, might be actually 2% away from where you think you should be. So you think you've got 25 cubic centimetres of solution, but you could be as much as 2% wrong. And that's due to the equipment that you've selected to use. And then as a second example, if we took a pipette and we measured the same volume, 25 cubic centimetres, this time the absolute uncertainty is plus or minus 0.06 cubic centimetres, so far better. We then divide it by the measurement, 25 still, because we're measuring the same volume of solution, and then multiply it by 100, and that gives us 0.24% uncertainty. So you can see from just these two examples that the selection of equipment is really important in terms of reducing that percentage uncertainty and helping us to be confident that the value that we are measuring is correct. Additionally, if you are measuring a change in something, for instance a change in temperature, using a thermometer that was accurate to the nearest 0.5 of a degree C, and let's say the first temperature that you recorded with your thermometer was 12.5 degrees C, and then later you measured 27.5 degrees C. So that is obviously an increase, a change of 15 degrees C. But the first measurement could have been out by plus or minus 0.5. The second measurement could also have been out by plus or minus 0.5. And so therefore, because you've taken these two readings, we need to multiply that number for the absolute uncertainty by 2 when we're calculating the percentage uncertainty. And so the calculation is 0.5 multiplied by 2 divided by 15, because that was the measurement, the change that we were deriving from those two different temperatures. And then we have to multiply that by 100, and so that gets us quite a significant error of 6.7%, because we end up with 0.5 times by 2, which is 1, divided by 15 times by 100, which is 6.7%, which is a large percentage error on this occasion. Sometimes it's necessary to quote the total percentage uncertainty for an experiment, and to do that you simply sum the individual percentage uncertainties for all the different readings that you made during that experiment. So suppose an experiment involved those three readings that we've already mentioned: the 2% error from a measuring cylinder volume, the 0.24% error from a pipette volume measurement, and a 6.67% error from the temperature change reading. And so all of those numbers added together gives us a total of 8.91% error. And so that's actually really bad, because that's quite a high value. And so that means that we've calculated a value, we've maybe worked something out at the end of it, but our equipment is saying that we could be 8.91% out as a result of those three different readings. We can see from looking at those three values that the temperature change has got the greatest percentage uncertainty tied to it, but when you're making multiple different readings in different ways, the total percentage uncertainty is the sum of all those individual values. You can be sometimes asked, how would you reduce the percentage uncertainty for a particular procedure? Now, obviously, to an extent, that depends on what the experiment involves. You know, is it a titration? Is it a calorimetry experiment? So the answer that you give might vary. But really, our answer is going to reduce down to two particular concepts. And to explore those, let's just take a look at the equation that we use to calculate the percentage uncertainty. It's the absolute uncertainty divided by the measurement that we're making multiplied by 100. Well, you can see that the 100 is always going to be there. So the only two terms that we can affect are the absolute uncertainty and the measurement. So the absolute uncertainty depends on the equipment that we're selecting to use. So if we use a more sensitive piece of equipment with a lower absolute uncertainty, our percentage uncertainty will decrease. However, the catch is often questions say, without changing the equipment, how could you reduce the percentage uncertainty? And what that means is we can't touch what's on the top there. That absolute uncertainty is fixed. So the only thing that we can do is adjust the measurement. And so to make the measurement result in a smaller percentage uncertainty, we have to be making the measurement bigger. And so whatever change we are going to cause to happen in our experiment has to result in a larger measurement for our whatever it is that we're doing. So a larger temperature change, for instance. And so if we're going to get a larger temperature change, well then maybe we use a more concentrated solution because that will result in more heat energy being released and therefore a larger temperature change. So any change that we suggest to our procedure has to result in a larger measurement. For instance, as I say, an increase in concentration leads to a larger temperature change, and that will, of course, give us a smaller percentage error because the number on the bottom of the expression is getting larger, and so overall a smaller outcome when we do the calculation. Another question that you could be asked that is quite common is, was the experiment accurate? Which at face value is a bit of a funny question and a bit of a vague question, but what they want you to do is explore two particular things. They want you to consider what the total experimental percentage uncertainty was. So that's, for instance, the 8.91% value that we calculated on the previous page. And what that means is that the equipment allows us to be 8.91% away from where we think we are, just through no fault of our own, through the equipment's uncertainty associated with each of those individual readings. And then the second thing that we need to consider is how far are we away from where we should be? So in other words, what is our percentage accuracy? And so if our percentage accuracy is, say, 5%, that means we're 5% away from where we should be. That doesn't sound great, really. But if our equipment percentage uncertainty is 8.91%, then that means we are within tolerance, so to speak. We are closer to the true value than our equipment uncertainty allows, thereby saying that this experiment is actually accurate. On the other hand, if we were, for instance, 12% away from the true value, that our accuracy is we're 12% too low, say, and then when we consider it against the 8.91% equipment uncertainty, then we are outside tolerance. We are further away from the true value than our equipment allows us to be. So on this second occasion, we would say that our experiment was not accurate because we were further away from the true value than the percentage uncertainty from the equipment would suggest that we should be. Now we're going to take a look at those questions I mentioned earlier. So in these 6 questions, we explore the different ways that percentage uncertainty can be asked about. In this first question, we're asked about a temperature change, and we're told what the temperature starts at and what it goes to. So this is endothermic, but that's not necessary for this question. But the temperature change is 2.6 degrees C. That's the difference between those two numbers. They're telling us that each reading has got an uncertainty of 0.1 degrees C. When they say each reading, that is signposting the fact that multiple readings have been made, and so that absolute uncertainty is going to need to be multiplied by the number of readings that were made, and we can see here that there were 2. And so the calculation that we need to do here is 0.1 multiplied by 2 times by 100 and then divided by that temperature change, which is 2.6. And when we do that, we get 7.69%, which rounds to 7.7%, which means D is the correct answer. Similarly, question 2 involves a change as well, because what we're doing is we're adding some solute to a volumetric flask. And we're shown here that the mass of the container with the solute is 10.13 grams. Then that solute is removed and put into the volumetric flask, and the container now is 4.48 grams. And so the mass that's been added to that volumetric flask is the difference between those two, 5.65 grams. We're signposted again to the fact that each of the readings has got a particular uncertainty, and we know that there were 2 readings that were made, And so the percentage uncertainty is this absolute uncertainty multiplied by 2 for the fact there were 2 readings, divide by that measurement, 5.65 grams, and then multiplied by 100. And when we run those numbers, we get 0.177%, which of course is 0.18 to 2 decimal points, which means C is the correct answer. Question 3 is a little bit different. Question 3 gives us the uncertainty and the percentage error and asks us what the minimum volume of liquid that can be measured is. And so we're working out what the measurement is. So if we substitute these numbers in, we've got plus or minus 5 divided by m, our measurement, multiplied by 100 is equal to 0.2. If we then multiply both sides of the equation by m and then divide both sides of the equation by 0.2, we're left with m, our measurement, is 5 divided by 0.2 multiplied by 100. And when you calculate that, you get 2,500 cubic centimetres. But if you notice, all of these values are in cubic decimetres, so we need to divide our number by 1,000 to get 2.5 cubic decimetres, which means that C is the correct answer. Question 4 is a nice straightforward reading question. We've been told that the absolute uncertainty is 0.01. We are recording 0.25 grams, so the percentage uncertainty is found by dividing those numbers, multiplying it by 100, and we get 0.4%. So B is the correct answer here. And then the final multiple choice question is a tricky one because we've been asked which of these pieces of equipment has got the smallest percentage uncertainty. Now, when faced with a question like this, we've got 2 choices. Choice 1, calculate all those percentage uncertainties, and you might prefer to do that. So that means take the absolute uncertainty that you've been given, divide it by the measurement, and multiply it by 100. And you can do that, and that will get you the right answer. But you only have got about 1.7 minutes per multiple choice question, so cutting corners is a preference. We can see, by the way, for my percentage uncertainties that I've calculated, that A is the correct answer. But how could you get to A a little bit faster? Well, first of all, we don't actually need to calculate the percentage uncertainties. We just need to know which one's smaller. So given that in my calculations I've multiplied them all by 100, why don't we not do that? Why don't we not multiply any of them by 100? And we're just left with the fraction. And so first of all then, for A, we've got 0.1 divided by 25. And for B, we've got 0.5 divided by 25. And clearly B is going to be larger because 0.5 is larger than 0.1. And so we can immediately rule B out. And therefore A is looking good. Then when we look at C, we've got our mass recording, and we've got 0.001 divided by 0.15. That's our fraction. And then for D, our fraction is 0.1, the uncertainty, multiplied by 2 because of the change. That's why I did that over on the right-hand side as well. And so 0.2 divided by 23.2. So what we've now got is 3 fractions that we're going to actually calculate, and then we're going to look at the value which is the smallest, and that is of course going to be A, whichever way we do it. So you might prefer to calculate the percentage uncertainties as I've done on the right hand side, but I would recommend trying to go for a shortcut method because obviously it's going to be faster for you in the long run. And then the final question is just 2 percentage uncertainty calculations, one using a pipette, and 25 cubic centimetres of solution was measured with the pipette. So we're going to do 0.05 divided by 25 times by 100, which gets us 0.2%. And then with the burette, we're told that 24.25 cubic centimetres have been measured using the burette. So 0.15 divided by 24.25 multiplied by 100, which gives us 0.619% or 0.62% to 2 decimal places. Okay, that's the end of the calculations. That's the end of the video. Complicated topic. Hope it's a lot clearer for you now. I'll see you again soon.